Hi, classes number 1 and 10.1. So in last section, we we believe something true to be about a population. Then we took a sample to see if that sample really matched what we believed about the population, or whether it supported another claim or other evidence. And this time, what we're going to be doing in chapter 10 is that we have two different populations. So like population 1 and population 2. And we are going to take a sample from both of those populations. And then we're going to assume that those populations came from like they have the same mean. In other words, they're sort of coming from the same one big population, and they kind of have the same mean, or sometimes the same proportion. And what we do is we do a distribution instead of the sampling distribution. We actually do a sampling distribution, but then we do a sampling distribution of the difference of these two. If it's a proportion problem, it's two proportions, or a sampling distribution of the difference of the two means. So in the null hypothesis, we assume that the two means or the two proportions are equal. So when we do the sampling distribution, these are actually differences. So it's like the mean one for the first population minus the mean the second population. But that's actually where, in the null hypothesis, we're assuming that those two are equal. So if I take away the number minus itself, we just get 0. So the distribution it's 0, and then what happens is we take a sample from the first sample, like X bar, we call it the first, well, I'm thinking about the mean. I'm explaining like it's a mean problem. And it is a mean problem, okay. And then we take a sample from the second population, we subtract them, we see what that value is. And basically, if that value is way out far in the tails here, it's not a common difference to get, because there's a distribution of all the differences. If they came from the same population, if they came from populations of the same mean. If you want to say it that way, if the difference in these means is really large, then it's evidence that they didn't come from the same population, or at least they didn't come from populations with the same mean. So if we have a difference way out here in the tail, then we calculate the probability of me getting a difference as that large or larger. So and then we're going to say, hey, it's really unlikely to get a difference like that unless they came from two populations with two different means. So then we reject the null hypothesis that means are the same, and then we say there is sufficient evidence to say that the means are different, or the situation is. So that's where, instead of looking at the sampling distribution of just the sampling by itself, we're looking at a distribution of the difference of the mean of the means. Okay. That's the biggest difference here in this section, but all the steps are going to be kind of the same. The entering into the calculator is going to be a tiny bit different, but it's going to be very similar to last chapter. So it says the U.S. Center of Disease Control reports that in 1990, the mean life expectancy is 47.6 years for whites and 33 years for non-whites. Suppose a survey of randomly selected death records for whites and non-white people born in 1990 from a certain country is conducted. Of the 114 whites surveyed, the mean lifespan was 47.2 years, and the standard deviation was 11 years, and the 92 non-whites, the mean lifespan was 36.5 years with a standard deviation of 15.2. Conduct a hypothesis test at the 0.01 level of significance to determine whether there is no difference in mean lifespan in the countries for whites and non-whites in the year of 1900. So They say, is it safe to assume that the number of whites that were sampled is less than 5% of all the people, white people born in 1900? And think with, like, if we're talking about the United States, so how many did they sample? They said they sampled 100, they surveyed or sampled 114 people, and that's not a very big number. So I'm thinking that's going to be less than 4 or 5% of all the white people in like a particular country. That's definitely going to be less than 5%. So they don't actually give us the number of white people in the country, which they should have, so we can actually really calculate but it's not a big deal. Okay, then the number of non-white people less than 5%. That's probably definitely true as well. So we're just going to wave our hand and just kind of say yes to this, to the question, this early question. Then they say, is that now in order for another prerequisite preliminary question that we have to ask is that the number of white people sampled, is it greater than 30? And so they said it is 114, so it is greater than 30. And then the number of non-white people is that 922. No, sorry, 92 non-whites. Okay, so I think we surveyed, the mean life was okay. And of the 92, yeah, so non-whites, okay, so like there was 92 non-whites sampled, so that also is greater than 30. So we have a yes and yes on both of these two questions. And then the next step is determine the null hypothesis. So here, the null hypothesis is almost always equals. However, once in a while, it'll be the opposite of what your alternative hypothesis is. So let's focus on what the alternative hypothesis is. Suppose a survey of randomly selected death records and non-white people from a certain country is conducted. Conduct a hypothesis test to determine whether, okay, so here's what we want to determine what? To determine whether there was no difference in the mean lifespan for country white and non-whites. So no difference means not equal. So that one's tricky because we don't see here a more than or greater than, or we don't hear anything like that. So when they just say if there's no difference, they mean not equal. So for the alternative hypothesis. Well, if there's no difference, then it'd be actually, no difference between the two populations would be equal. But the equals has to always be in the null hypothesis. So it's kind of like we have to test the opposite of what they're claiming to test, and that is that they're not equal. So we do not equal for I can't do equals in the alternative hypothesis. That's just, we cannot do that. It always has to be equals in the null hypothesis. So anytime that it seems like the claim is, are they equal? You always have to put the alternative hypothesis is not equal. Okay. All right, because basically that's just saying, when we're testing the same thing and just saying it in a different way, right? Like you could say, is it equal? Well, the opposite of being equal would be not equal. So we're gonna see whether there's evidence more for there being equal or whether it's not equal. See if it's not equal, if there's not evidence that they're not equal, then it's leaning towards them like they're equal, and this will be evidence that it's equal if it's not equal, right? So it'll work out. This test will work out. Okay, so we have the null alternative hypothesis. Now we just have to enter all of this information into the calculator correctly. And so we're going to have information coming from the first sample. Let me put that, and that's something important here. When they have this, what I like to always do, see, they have the mean of the white. So I'm going to call that my population 1, because they always put 1 on the right in the null hypothesis. Population 1. So I'm going to call the white population my population 1. Okay, and then the other population my population 2. That doesn't matter so much here because it's a just not equal test, but like it will matter later if this was a greater than or less than test. Okay, so this information from the first sample. This is the number sampled for the population 1. This is the, okay, the mean life was, so this is the mean, and that's the standard deviation all for population 1. Then for population 2, here's your N2, here's your mean, and here's your standard deviation for that second sample. And that's basically everything we need. Okay. All right. Oh, now we need to go to class calc to do this. All right, because this is a mean problem, we're going to do, and because this is 2 samples that they're comparing, we're going to do a 2-sample t-test. Go to stats, and then I go to tests, and then 2-sample t-test. Okay, so then all they need is the information from the samples. So we just enter in. I think did I write down, this is the hardest part, is like me trying to enter this data. Kind of easier if you're using a TI-84 calculator. Okay. So from population 1, I do the 114. And then see, it says X bar 1, which means the mean from sample of population 1. SX1, the standard deviation from population 1, which is, I'm calling the white population. Okay. The mean, oh wait, I'm messing up. That's the number, that's the N. So the mean was 47.2. Standard deviation was 11. And the N was 114. Good. Now the mean was 36.5. Catching if I'm doing this wrong. And standard deviation 15.2. This is so easy to mix up all these numbers. Yes, okay, and then 92. Okay. Now I just have to remind myself, because this class calc gives you the answer for everything, whether it's a left tail, right tail, or not equal to tail. So in this case, it was a not equal. So this is our p-value that we want here, and this is the test statistic. So I can't even see this. I need to expand this out, I guess. I don't know how to. Usually we pick not polled. See how they say polled and not polled? So we could like click this button to say polled. Usually when we calculate this, we do not polled. So, so there's our answers. T is 5.6. Let's go down. T is 5.6609. That's exact. That's what we want. And then p-value is 0. And notice how as soon as I saw that this one was 1, it says 3.37, but I know it's 3.37 times something to the 10th power. So if this is 1, this is going to be practically equal to 0. So it's probably like times 10 to the negative 8 or something like that. This is probably very small as well, because this 2-tail is actually the double of this single tail test. So that's why 3.37 and double of that is 6.7. So it seems like this is, since this one's 1, I mean, because this is the other area under the curve. So if this one's practically 1, this is practically 0. So that's why they're saying I'm kind of, let me see if I can get it to show me the actual answer, because it's cutting off the answer here, and I don't know quite how to make it show me the whole answer. It says I can barely see it saying 10 to the negative something, so it's probably like negative 10 or something. And I'm not quite sure. Maybe I can expand this out. I don't know how to get it to show me that full answer. Or Well, hopefully the TI-84 calculator is a better calculator for that. But the big indication here that I knew it was 0 is because that one's practically 1. And these two together would add to one whole, because this is a left, that's a right, this is a right left tail test, that's a right tail test. So this is at the end. This is all the area under the curve to the left, and that's the area curve to the right. So those two together should equal 1. And when we're saying that one side by itself is 1, then the other side is really, really tiny, tiny, practically 0. And that's what they're saying in p-value 0 here. So if you're using the TI-84, they probably actually show you times 10 or EE times negative something. So you don't have to stress about, which is making me angry. I cannot actually see the actual answer here. And that's kind of frustrating. But you can kind of see it's 10 times negative something. I wonder, I'm sure there's probably a way that I can see it, but maybe if I click share. Well, whatever. Okay, so well, we know it's practically 0. So our p-value is 0. Then because we have such a low, they say if the p-value is low, then null hypothesis must go. So the p-value is 0. That's low. That's lower than whatever low we say we're gonna, that's lower than any alpha they give us, right? And this situation, it is the alpha is, they even give it to us? Oh yeah, 0.01. So of course 0 is smaller than that. We knew that was going to have to take place. So we reject the null hypothesis, and then there is sufficient evidence to support the claim that whites and non-whites have a different mean lifespan. So they're just, all they're saying is there's evidence to support, and you just restate whatever your alternative hypothesis is. So anyways, please let me know if you have questions about this, and have a good day. Bye.